All right, the next thing we're going to talk about is example 7, which we kind of walk through, and this is the divergence of the harmonic series. So this series, adding up all terms of the form 1 over n, where our index starts with an initial value of 1, this series is called the harmonic series. So this is a famous example, it's a famous counterexample, and it's a really just strange and powerful example of how weird infinite series and things can be, how counterintuitive they can be. Sometimes they're very intuitive, sometimes they're a little counterintuitive, and the divergence of this particular series is definitely one of the more counterintuitive things you'll come to find and experience in Calc 2. So this series actually diverges. So even though we're adding up numbers that are getting smaller, this series still diverges. So far, everything else we found, if the numbers are getting smaller, they've converged. So what this actually tells us, the fact that this series diverges, it tells us that it's not just enough for the terms of the series to get small and approach 0. They need to do it in such a way that it happens rapidly enough. So the fact that you get closer and closer to 0, that's not good enough. You have to get closer to 0 quickly enough. So what we're going to do is look at some of the partial sums. So there is a theorem in mathematics, in analysis, that no matter what sequence you have, so given some sequence, a sub n, any sequence at all, it may converge, it may diverge. So given some arbitrary sequence, this sequence has a convergent subsequence. What this means is if you write out a list of numbers, a sequence. So if I just start by writing out different numbers, maybe this thing doesn't converge to anything, maybe it does. I just start listing out numbers. I could then, from this sequence, create a new sequence. Let's call this sequence a sub n. I can create a new sequence from here, call it a sub n sub k, so the subscript has a subscript, and maybe I only select every other one. So when I take a sequence and select via some scheme, any scheme, maybe I pick every other one, maybe I skip the first term of the original sequence and then keep all the other terms. That is a subsequence because I'm selecting some subset of the original sequence's terms in some order, right? So if I do that, then I have a new sequence. 3, 1, 4, 2, a half, 3, 1. Yada, yada, yada. So every sequence has a convergent subsequence. So this means given any sequence, I can find within it a sequence that converges. Okay? There's a related fact, and that is if a sequence actually does converge, then no matter what subsequence you find, that subsequence also converges to the same limit as the mother sequence, so to speak, the parent sequence, the original sequence. So if you have a sequence and you don't know whether or not it converges or diverges, if you find a subsequence from that sequence that diverges, then that means the parent sequence, the original or the bigger containing sequence, that sequence must diverge as well. Or you can even find two different subsequences. If they converge to different values, then that means the original sequence must diverge also. So here's the real fact here. So any subsequence, let's say A sub n sub k, of a convergent sequence converges to the same value as, so any subsequence converges to the same value as the sequence A sub n, the original sequence, i.e. symbolically, if A sub n converges to L, a limit L, then a subsequence A sub n sub k converges to L also. And this is what we're going to use here to explain and to show the divergence of the harmonic series. So from our list of partial sums, right, S1, S2, S3, S4, S5, so on and so forth, this creates a sequence of partial sums. From this sequence of partial sums, we could just take a look at a specific subset of all of these terms. So instead of S1, S2, S3, S4, so on and so forth in that order, we could just take a look at S1, S2, S4, S8, S16. So really just the powers of 2, right? 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 2 is 4, 2 to the 3 is 8, 2 to the 4 is 16. So this right here is technically a subsequence. So this right here is important. This is a subsequence of the sequence of partial sums. That's important. So if the sequence of partial sums converges, then this subsequence would also converge to that same value. So what we're going to do to prove the divergence of the harmonic series is we're going to show that this specific subsequence diverges. And since this specific subsequence diverges, that means the sequence from which it was picked or born from must also diverge. So because this is a subsequence of the sequence of partial sums, if this subsequence diverges, then the sequence of partial sums diverges, and that is the definition of divergence of a series. Okay. So what we're going to do is just write out these specific partial sums. So first partial sum is 1. Second partial sum is 1 plus a half. And let's take a look at S sub 4. Let's focus here because this is where it starts to get a little bit more interesting. So S sub 4 is 1 plus a half plus a third plus a fourth. Now, this right here is bigger than this term right here. What changed? This 1/3 got replaced with a 1/4. And since 1/3 is greater than 1/4, if we just swap out the 1/3 for a 1/4, leaving everything else the same, then we essentially made this new expression smaller than the original. And then we simplify this a little bit. A fourth plus a fourth is a half, and then a half plus a half is 1 whole, or in this case we're writing this as 2 seconds. So we've just shown that s sub 4 is greater than 1 plus 2 halves. So this implies that s sub 4 is greater than 1 plus 2 over 2. Now let's do this again for s sub 8 so we can kind of see why this is going to be useful for us. So again, we write out the full partial sum. 1 plus a half plus a third plus a fourth plus a fifth plus a sixth plus a seventh plus an eighth. And we get this whole expression. So right here is s sub 8. Now what we're going to do is exactly the same replacement we did earlier. So we're going to swap this 1/3 for a 1/4. So even that one swap makes this inequality appear. We replaced one of the terms with something smaller. So we've created something that is smaller already. But we're also going to do the same thing here with a fifth, a sixth, and a seventh. We're going to replace each of these three things with 1/8. And again, 1/8 is smaller than a fifth, a sixth, and a seventh. So that inequality is still true. It's still less than. And here's the kicker. Just like before, these 2/4 make a half, and together with this half, we get 2 halves. And then here, all of these eighths together give us another half. So we're really just building halves. Here's a half, here's a half, here's a half. So we have a total of 1, 2, 3 halves, together with this leading 1. So ultimately, we've just shown that s sub 8 is strictly greater than 1 plus 3 over 2. And notice here's a connection here. Remember that s sub 8 is exactly 2 cubed. So s8, or s2 cubed, is strictly greater than 1 plus 3 halves. And the same thing can be done here. S sub 16 is s sub 2 to the 4. And that is strictly greater than 1 plus 4 halves. S sub 32. 32 is 2 to the 5th. So s sub 2 to the 5th is strictly greater than 1 plus 5 halves. 64, that's going to be 2 to the 6th. So s sub 2 to the 6th is strictly greater than 1 plus 6 halves. So as a pattern, s sub 2 to the n is strictly greater than 1 plus this exponent n over 2. So this, what we've actually found here, we have found a lower bound for a subsequence. So s sub 2 to the n is a subsequence of s sub n. That's a fact. So that's fact number 1. Fact number 2 is that this subsequence is bounded below, strictly bounded below, by 1 plus n over 2. So no matter how far we go, we definitely know that this subsequence, this term of the subsequence is larger than this number. So then, here's the fact that we're going to use. If any subsequence of a convergent subsequence, this would have to converge to the same value as the original sequence. So, what this means is, this tells us, so if S sub n converges to some number, let's say, L, i.e. the limit as n goes to infinity of S sub n equals L, then the subsequence S sub 2 to the n must also converge to L. And what's important here is that this L is a finite number, right? Remember that when a limit exists, that means the limit is a finite real number. It's not infinite. So it converges to some finite number L. Then, if it converges, that means this any subsequence must also converge to L, i.e. the limit as n goes to infinity of S sub 2 to the n must also equal L. So really, we're saying that the limit as n goes to infinity of S sub n must be the same as the limit as n goes to infinity of S sub 2 to the n. So the limit of any, so if this converges, then the limit of any subsequence must also converge. And here's the issue. If we take the limit of the sequence, the subsequence, this is the limit of 1 plus, well, I guess here's what I should say. There's a little typo in my notes. This should be, the limit of this has to be greater than the limit. Has to be greater than this limit. That's a typo in my notes. So, if it's greater than that, let's figure out what the limit of this lower bound is. Well, the limit of this lower bound is infinity. So that means the limit of this subsequence must, if it's greater than that, it has to also be infinity. Because no finite number is greater than infinity. So this implies that the limit as n goes to infinity of S sub 2 to the n is infinity, which implies that the limit as n goes to infinity of S sub n is also infinity, i.e. the harmonic series diverges. So the specific reason is the fact that if the harmonic series converged, that means its sequence of partial sums converges to a finite number. And since a sequence, if it converges, that forces every single subsequence to also converge to that same value, we found a subsequence that diverges. So it's impossible for a convergent sequence to have a divergent subsequence. That's not possible. Because if the sequence is convergent, all subsequences converge to that same value. We demonstrated a subsequence that diverges. So that must mean the supposition that the harmonic series was convergent had to have been false. Therefore, the harmonic series diverges.